Hi, so this is lecture 14 of MA 221, and today we'll be discussing about the hyperbolic functions and derivative of it and how to do integration and stuff. Okay, so first let us define what is hyperbolic function. So for real x, for any real number x, define sine hyperbolic x to be half e to the x minus e to the minus x, and define cosine hyperbolic x to be half e to the x plus e to the minus x. This is called hyperbolic sine, and this is called hyperbolic cosine. Okay. So if you talk about the graphs, then the graphs for y is equal to half e to the x looks like this, and for the graph of y equal to half e to the minus x looks like that. And using this tool, we can sort of get the graph of hyperbolic functions. So hyperbolic sine, hyperbolic cosine will look like this. And hyperbolic sine will look like this. This is y equal to sine hyperbolic x. Okay. Okay, there are some remarks that I want to make here. Sine hyperbolic function is an odd function. So for odd functions, what do we know? We know that if it satisfies something like sine hyperbolic minus x to be minus sine hyperbolic x, if this minus inside the argument of function comes out, then we call that to be odd function. And for the other case, we call it to be even function. So sine hyperbolic is odd, but cosine hyperbolic is even. And also the third remark is when you take x to be infinity, then sine hyperbolic and cosine hyperbolic tends to half e to the x. Okay, cool. Now the next question naturally would be, what is the derivative of these functions? So we can just calculate using the definition. This is the definition for sine hyperbolic x, and then just do the derivative. It'll be something like this, right? But this is half e to the x plus e to the minus x, which is just cosine hyperbolic x. So we know that what is the derivative of sine hyperbolic x. Similarly, for the cosine hyperbolic x, we will do the same sort of thing. And if you do the derivative here, term by term, then you'll get the answer to be sine hyperbolic x. Okay, cool. And it is not difficult to guess that tan hyperbolic x should be defined like sine hyperbolic x over cosine hyperbolic x. This is called hyperbolic tangent. And sec hyperbolic x should be defined like 1 over cosine hyperbolic x. Cosec hyperbolic x is just 1 over sine hyperbolic x. And cot hyperbolic x should be 1 over tangent hyperbolic x, or in other words, cosine hyperbolic x over sine hyperbolic x. Okay, kind of similar to the trigonometric functions. And tangent hyperbolic x kind of look like this. Now we know that there are some identities for trigonometric functions. For example, sine square theta plus cosine square theta is 1. So similarly, we have some identities here as well. I will show some of them. So this is one identity. It's sort of similar to sine square theta plus cosine square theta to be 1. So you can just prove it by just using the definition as it is. And if you calculate this using the normal algebraic manipulation, at the end you'll get the answer to be 1. Okay, this is easy to follow, so therefore I'll not show it explicitly. Now for ddx of tangent hyperbolic x, I know what is tangent hyperbolic x. This is basically sine hyperbolic over cosine hyperbolic. And then this is just the rule for quotient functions. We know how to do the derivative of those functions. So this will be cosine hyperbolic square x, cosine hyperbolic x there, times ddx of sine hyperbolic x minus sine hyperbolic x ddx of cosine hyperbolic x. I know what is derivative of sine hyperbolic. That is cosine hyperbolic. And also I know what is derivative of sine hyperbolic. Which is sine hyperbolic x again. Okay. So on top I have cosine hyperbolic square x minus sine hyperbolic square x over cosine hyperbolic square x. But the top thing is just 1 by the identity that we just told. Okay. So therefore this will be 1 over cosine hyperbolic square x, which is same as secant hyperbolic square x. Okay, cool. Okay, in this page we have the the corresponding formulas for trigonometric and hyperbolic functions. So you can look at it later, I guess. So let me just do some of the examples. For example, if we have to find what is the derivative of sine hyperbolic inverse x, so I can take y to be sine hyperbolic inverse x. Then my goal is to find dy over dx, right? But what does this line say? This is just sine hyperbolic y, the same as x. Now, if I take derivative with respect to x, then what I'll have? Then I'll have cosine hyperbolic y and then dy over dx by chain rule. On the right hand side, I have just 1. Okay, cool. So therefore, dy dx is 1 over cosine hyperbolic y. But at the same time, I know that my question was in terms of x. So therefore, my answer should also be in terms of x as well, right? So therefore, I need to use cosine hyperbolic y minus sine hyperbolic square y to be 1, the identity. And then I know that cosine hyperbolic square y will be sine hyperbolic square y plus 1. And I also know that sine hyperbolic y is x. I took that. So therefore, this will be 1 plus x squared. And then cosine hyperbolic y will be just square root of 1 plus x squared. So this answer should be 1 over 1 plus x squared square root. Okay. So therefore, d dx of sine hyperbolic inverse x is 1 over the square root of 1 plus x squared. Now, as we know that integration and derivative was like reverse processes, so therefore I can take integration both sides. Then this integration and derivative will just cancel each other, and there will be just the function. So I can write integration 1 over square root of 1 plus x squared dx is same as sine hyperbolic inverse x plus c. Okay. Also, at the same time, I can write this as ln x plus square root of x squared plus 1 plus c. How? The reason is something like this. So say y is sine hyperbolic inverse x. Then I can write x to be sine hyperbolic y. But by definition of sine hyperbolic, this is half e to the y minus e to the minus y, right? Now, if I simplify, then 2x will be e to the y minus 1 over e to the y, right? This is basically manipulations. Then 2x e to the y will be e to the 2y minus 1, right? And this is same as e to the y square minus 2x e to the y minus 1 to be 0. Okay, now use quadratic formula. Then we'll get e to the y to be 2x plus or minus square root of 4x squared plus 4 over 2, right? And this is just x plus minus x squared plus 1. Okay. Now, we know that square root of x squared plus 1 is bigger than square root of x squared, which is just modulus of x. So x minus square root of x squared plus 1 is bigger than 0. So therefore, oh, sorry, it's a mistake. So x minus square root of, so from this line, what I can say is that x minus square root of x squared minus 1 is less than 0, right? Because no matter what is x, is it might be positive or negative, but anyway, x minus square root of x squared plus 1 is less than 0 because this quantity is always bigger than modulus of x. Okay. So therefore, and we always know that e to the y is bigger than 0, no matter what y is. So therefore, I can say that e to the y should be x plus square root of x squared plus 1. Because if I take the minus 1, the other root, then left-hand side will be negative and right-hand side will be positive, which should not be the case. So therefore, I should say that this is only root. Then I can say y is just ln x plus square root of x squared plus 1. Okay. So therefore, I know that I can write y is equal to sine hyperbolic inverse x. Also, this is same as ln x plus square root of x squared plus 1. Yeah. So therefore, we can see that I just replaced sine hyperbolic inverse x with the other quantity there. Okay. So comparing all these two lines, this line and this line, I can say that these two things are equal. This thing and that thing is equal. Okay. I hope things are a little bit clear. Okay. Cool. So using the same kind of manipulation, I can write sine hyperbolic inverse x is ln x plus square root of x squared plus 1. Basically, I have proved this for x belongs to R. And similarly, by doing the same kind of manipulation, we can say that this will be ln x plus square root of x squared minus 1, where x is bigger than or equal to 1. And also tangent hyperbolic inverse x is half ln 1 plus x over 1 minus x. Cool. You can prove it if you want. The next question should be, is there any relation between the trigonometric functions and their hyperbolic counterparts. The answer is yes, there is a relation. I know that e to the ix, this is coming from complex analysis, but this is same as this quantity. For example, e to the I pi is cosine pi plus I sine pi, which is basically -1. So and the proof is basically uses some Taylor series, I guess, but we'll not go into that. E to the ix is cosine x plus I sine x. If you take e to the minus ix, then you'll get cosine minus x plus I sine minus x. But we know that cosine is even function, so therefore this will be just cosine x. But sine is odd function, so therefore the minus inside will be carrying out. And then I'll have this. So you can see that cosine x will be half e to the ix plus e to the minus ix, which is basically cosine hyperbolic ix. And sine x, by the similar kind of logic, is 1 over 2i e to the ix minus e to the minus ix, which is sine hyperbolic ix. There should be a 1 over 2, right? Rather, it should be 1 over 2i, I guess. Oh no, I'm wrong there. So let me just try to simplify things. Okay, so this is just 1 over I sine hyperbolic ix. Yeah. Okay. So far, these were the ingredients that you might need to solve the further, complicated examples. So I'll solve some of them. Say the next example is cosine hyperbolic 4x sine hyperbolic to the third x dx. You want to get this integration. So sort of like same ideas, from this kind of integration where you have only trigonometric functions will follow here as well. So I can see that there is a odd power in sine. So if you remember, the rule was to save 1 sine hyperbolic x and do a substitution u to be cosine hyperbolic x. Okay. So I may just write hyperbolic integrals similar to approach. As trivial. Okay. So now take u to be cosine hyperbolic x, then du is basically sine hyperbolic x dx. And also we know the identity cosine hyperbolic square x minus sine hyperbolic square x is 1. So sine hyperbolic square x is just cosine hyperbolic square x minus 1, which is u square minus 1. Now put everything in the integration. Cosine hyperbolic to the 4x times sine hyperbolic square x times sine hyperbolic x dx. The same integration I have written down with a sign apart. And now use the substitution u to the 4 times u square minus 1, because sine hyperbolic square is u square minus 1. And then I know that du is just this quantity. So this is du. Okay. Okay, now this is quite easy. E to the 6 minus e to the 4 du. So I'll have u to the 7 over 7 minus u to the 5 over 5 plus c. Now put back u as cosine hyperbolic x. So I'll get this minus to the 5x over 5 plus c as my answer. So things actually follows quite nicely as like the trigonometric integrations. Okay. Now, okay. So we know that how to do trig substitution when we have this sort of integrations, right? If we have this sort of terms in the integration, we know how to deal with those, right? Basically, we use x to be a sine theta in this case, and use the substitution, use the identity 1 minus sine squared theta is cosine squared theta. For the other case, we use x to be a tangent theta, and then use tangent squared theta plus 1 to be secant squared theta. For the third type of integrations, where we have this sort of radicals, then we use x to be a secant theta, and the identity that we use is this. Okay. Yeah. Similarly, for hyperbolic substitution, the identities that we use most of the time is cosine hyperbolic square x minus sine hyperbolic square x to be 1. And for when we see this type of radicals in the integration, we try to use x to be a sine hyperbolic theta and use the above identity. And when we have this sort of radicals in the integration, we try to use x to be a cosine hyperbolic theta and use the identity star. Okay. Yeah, let us see one example. How can we do the same sort of integration using hyperbolic substitution? So say the question is you have to find dx over square root of 1 plus x square. Okay. I know that cosine hyperbolic square theta minus sine hyperbolic square theta is 1. Okay. So I have square root of 1 plus x squared. So I should take my x to be 1 times sine hyperbolic theta, right? Then my dx will be cosine hyperbolic theta d theta, and square root of 1 plus x squared will be square root of 1 plus sine hyperbolic square theta, which is just cosine hyperbolic theta, right? So therefore, the integration sort of becomes, this integration becomes cosine hyperbolic theta, right? Dx is cosine hyperbolic theta d theta over cosine hyperbolic theta, right? So this is basically d theta. So theta plus c. Now what is theta? Theta is basically sine hyperbolic inverse x plus c. So that's an answer. So instead of hyperbolic substitution, if we have used, say, trig substitution for the same problem, then if you remember, we should have used x to be tan theta. Then the integration will become sec square theta d theta over secant theta, because I know that dx is just secant square theta d theta, right? And then 1 over x square will become like square root of 1 plus tan square theta. This is secant theta. So that's why on the top we have secant square theta d theta, and on the bottom I have secant theta. But then this is basically sec theta d theta. Now integration of that will be log secant theta plus tangent theta plus c. Now if you calculate, secant theta is basically square root of 1 plus x square, and tangent theta is x plus c. So I have this answer when we use the hyperbolic substitution, and I have that answer when we use the trigonometry substitution. But remember, somewhere I have proved that these two things are equal. Here, see, we have shown that these two things are equal. So hyperbolic x is same as that. So therefore, we are good. You can use the hyperbolic substitution and trigonometry substitutions. The answer are in sync. Okay. One more example of this radical, integration would be something like this: x squared dx over square root of x squared minus 16. This is nothing but x squared minus 4 squared, square root of that. So I can again use cosine hyperbolic square x minus sine hyperbolic square x to be 1, this identity. And I can use the substitution as x to be 4 cosine hyperbolic theta. We should have used theta. Okay, then dx will be just 4 sine hyperbolic theta d theta, and square root of x square minus 4 square will be just square root of 4 square cosine hyperbolic square theta minus 4 square. And basically this is just 4 sine hyperbolic theta. And now if I use this substitution, if I substitute everything on the integration, then I'll have integration 4 square cosine hyperbolic square theta over 4 sine hyperbolic theta, and there should be one more 4 sine hyperbolic theta d theta. Okay, and this is basically 16. That cancels and gives you cosine hyperbolic square theta d theta. Okay. Okay, so now this is interesting. Now, if we have trigonometric function instead of hyperbolic function there, you should have used reduction formula, right? Here also we have the same counterpart. So the reduction formula for hyperbolic functions are like this. If you have cosine hyperbolic to the n theta d theta, then the formula is 1 over n sine hyperbolic theta times cosine hyperbolic to the n minus 1 theta plus n minus 1 over n integration cosine hyperbolic to the n minus 2 theta d theta. So for n equal to 2, I have integration cosine hyperbolic square theta is just will be 1 over 2 sine hyperbolic theta cosine hyperbolic theta plus 1 over 2 again integration 1 d theta, because cosine hyperbolic to the 2 minus 2 is just 1. So this is half sine hyperbolic theta times cosine hyperbolic theta plus half theta plus c. Okay. So therefore, if I put that in my last line of the integration, then I'll get something like 8 sine hyperbolic theta times cosine hyperbolic theta plus 8 theta plus c star says that. And now, again, I had to just use the substitution to get back my answer in terms of x. So I know that my cosine hyperbolic x is x over 4. So I'll get 8 times x over 4. And then for theta, that will be um, cosine inverse, cosine hyperbolic inverse x over 4, right? Plus c. There is 8. I just have to put the value of sine hyperbolic theta. So sine hyperbolic theta is just sine hyperbolic square x minus 1. So sine hyperbolic theta is basically square root of cosine hyperbolic square theta minus 1. So it will be square root of x squared over 16 minus 1, right? Yeah. So that's my answer. Let me write it clearly. This is basically a like rough answer. I can write one more line. 4x, 2x square root of x squared over 16 minus 1 plus 8 cosine hyperbolic inverse x over 4 plus c. So this is the answer, yes. And for the sake of completion, these are the other two reduction formula for hyperbolic functions. I hope that you do not need anything more to solve the problems in homework 4 regarding hyperbolic functions. But still, if you feel some difficulty in solving those, let me know. Meet me in the office hours. Yeah. The idea will be like, using the same sort of tricks as we have used in normal trig functions or like normal substitution, trigonometric substitution, or like reduction formula exercises. But just that here you have hyperbolic functions instead of those trigonometric functions. Yeah, so that's it. Thank you.